The Alps are a classic playground for structural geologists and tectonic geologists. They've seen research for well over a century, not least because the Alpine chain is rimmed by a whole series of universities, so local geologists have been able to get on the rocks really easily. It remains a really important place for understanding how rocks deform in an orogenic situation. So let's go and visit some rocks. What we're going to do is we'll start by looking at the tectonic setting, and then we'll take a tour of structural styles. One of the things we want to contrast is the types of deformation that occur in basement, that's the crust, and the sedimentary cover that was deposited on top. So where are we talking about? Well, here are the Alps. They're the mountain range that lies on the northern end of the Italian peninsula, separating it from the rest of Europe. Let's zoom in and in. So tectonically, the Italian peninsula is referred to as Apulia. It's a microcontinent. Some people consider it to be a promontory of the African continent, and it has collided with the European continent, that's the rest of Europe, and the Alpine chain has been formed as a consequence of this collision. So here's a really simple cartoon of that collision process. So the Apulian continent has been rammed a little bit over the European continent, and the Alps are the debris caught in the jaws of this vice. Well, this is still a simple cartoon, but it still shows the idea. And the European crust has been stacked up and thickened. Some debris, which represents the former continental margin of Europe and various oceanic rocks, have been caught up in between that stacked European crust and the Apulian continent, which consists of crust and mantle lithosphere. In terms of terminology, the European or western side is generally referred to as the foreland, and the Apulian side, the Italian side, is the hinterland. And so this deformation could be split into an external part of deformation that's out there on the western side towards undeformed Europe, and an internal part of the Alps, which, as we all see, has got really complicated deformation lying in the heart of the mountain range. Well, we're going to take a tour, and we'll start off here in the external parts of the Alps. So let's go and have a look at this region from a view here on the edge of those range of hills. Here we go, and we can see that they're wooded ridges. These, as we'll see in a minute, are anticline crests, and they're separated by low-lying ground with those fields in, which separate the anticlines. Most of those fields lie in an area called the Annecy Basin, and out there to the west, to the left, are the Boogie Hills. Well, what happens at depth beneath these ridges? Well, they appear to be detached on thrust faults that stack up the strata. And this is what these fold structures look like at outcrop. Fairly broad, open structures, the layering, these are limestone beds that simply go up and over in the hanging wall to thrust structures. Well, these ideas go back a long way, and perhaps they're best represented by the work of Auguste Buxtoff in the early part of the 20th century. Here's one of his cross-sections from the Swiss part of the region. And he's showing thrusting of various sedimentary units. These cross-sections were based largely on surface geology together with railway tunnels which were excavated through these parts of the Alps. Here's another one of his cross-sections. And the structural style varies from section to section. In the lower one, it looks fairly straightforward and thrusting. In the upper profile, you can see more upright folding. There's thrusting as well, and some of those folds have folded the thrusts. But overall, the structural style is pretty straightforward. The key feature is that the deformation only involves the sedimentary cover, that is Jurassic and Cretaceous in age here, that is detached from the underlying crystalline basement along a weak evaporite horizon, and this has been encountered in boreholes. And there's some core on the left that's been recovered from one of these boreholes, showing highly sheared halite and gypsum evaporite minerals. And these weak horizons have permitted detachment of the cover strata from the underlying basement. So the structural style here comprises thrusting and nearly concentric folding. As we've seen, that deformation involves the strata that overlie this Triassic evaporite horizon. And in the case of the structures we've looked at so far, these sedimentary cover rocks are almost exclusively limestones, a stacked pile of platform carbonates, and they make for very simple large-scale structures. This region is known as the Juror. And here's an example of one of these structures in outcrop, seen on a hillside here of several hundred meters high, simple folded and thrust limestone layers. The deformation in the Boogie Hills in the Jura continues to the west, and it continues out as far as the salt horizon continues too. But out on the margin of the Brest Basin, the salt horizon has been dropped down, so it can't be accessed by the thrust detachment, and this controls the edge of the mountain belt on the margin of the Brest Basin. Well, so much for the edge of the Alps. Let's go a little bit further in. And as we go into the Alps, that's generally east and south, the deformation increases. Let's look at the style here. Well, in the Born Massif, a range of hills, you can see deformation that again, here's upright folding of limestones forming these rather spectacular folds. That's about 1,500 meters of hillside we're looking onto there. So as we'll see in a second, the deformation style will change as we go from the Jura into the next part of the Alps, the subalps, because the strata change. Rather than being a stacked pile of carbonates alone, which characterize the stratigraphy of the Jura, in the subalps, these thick carbonate units are separated by weaker claystones, mudstones and marlstones, so incompetent units that separate competent beams of limestone. And this changes the structural style. So the limestones make these spectacular folds, some of which are recumbent structures, as we can see on this Alpine structure near the town of Sallanches. And again, there's quite a big hillside there. We're looking at maybe 1 kilometre of vertical relief. So this fold sits within a pile of strata that are folded and thrust. On this cross-section, only the major limestone layers are coloured in. The white areas represent the incompetent units, the finer grained rocks. So we have a distinct structural style change as we go from the Jura into the subalpine chains. And the deformation has changed too. You can see that towards the base of this structure, the rocks become highly attenuated as they fold over and become overturned. So in this position here, we have some conglomerates, limestone conglomerates here, that are deformed, and we can see that the classa elongate in the direction pointed by the pencil there. So there's a distortional strain as well as folding experienced by the rocks in this region. So that was a quick look at deformation within the sedimentary cover in the external zones. Now the external zones are separated from the internal by a really major tectonic structure called the frontal Pennine thrust. Let's look at the shearing associated with this structure up here in the mountains near the town of Briançon in the French Alps. And here we've got a group of students doing some structural work in the outcrops. Let's see what they're looking at. Really sheared and deformed rocks. These are limestones in the grey rocks, which have got these spectacular tight fold structures in, and they're encased within that highly cleaved siltstone and sandstone. So strong deformation along the frontal Pennine thrust. It's a shear zone. So let's cross now into the internal zones, and we're going deeper into the Alps now. And now the rocks show intense ductile deformation. We've got breccias and conglomerates here that are entirely streaked out. so intense ductile deformation. The folding style also changes. Well, you can turn your back on it, but it'll still be there when you turn round again. Here are some pretty spectacular folds in limestones, now marbles. And we can see another example here. And here is a fold structure in quartz sandstones. Now, quartzites, that cliff section we're looking at there maybe is 30 meters high, so that's quite a big fold. Let's just pick out the layering in both of these examples, and we can see that these are similar folds. So the hinge areas are greatly thickened compared to the limbs that are thin and attenuating. So similar folding is the folding style within these sheared and deformed rocks. And some of this deformation get pretty intense. This looks like it's maybe just a set of alternating grey limestone layers or marble layers within a siltstone, but actually if you trace the layering out, you can see isoclinal folding. So really intense deformation when we get into the internal parts of the Alps. And the folds can become refolded too. So if you trace the layering around these structures, you can see really tight folds that are refolded. So complex folding, ductile deformation. And it's that characterises the internal zones. So as we've gone on our little tour from the outer part of the Alps on the western side out towards the European or stable European foreland, we came to the Jura, then into the subalps, and eventually crossed the frontal Pennine thrust into the internal zones. And as we did so, there was increasingly ductile deformation. So that we have concentric folding and thrusting out in the west, there's shearing along the frontal Pennine thrust, and then intense similar folding and refolding as we go into the internal zones. This implies that as we go across from the outer into the internal Alps, that during the deformation, the temperature was hotter for those rocks that are in the internal zones. They could behave in a more ductile fashion. And this in turn implies that the internal zone rocks, in order to have been hotter, were once more deeply buried than their external zone counterparts. So we can explore this in a really simple cartoon. So the external zone rocks were out there, but the internal zone rocks were buried presumably under a thrust sheet or major thrust sheets, perhaps the Apulian rocks in orange that had overthrust the European margin, providing the burial so that the rocks, when they were deforming in the internal zones, were buried and warm. Well, we concentrated by looking at the sedimentary cover, but let's now look at the behaviour of the basement. This is the crystalline rocks that in an Alpine context represent everything that is pre-Triassic in age. These were metamorphic and metaigneous rocks that existed before the Alps were formed. So we're going to contrast basement from cover. Well, let's return to our cross-section to the external zones, to the Jura and subalps, and the basement beneath them is not deformed. Rather, the thrust belt that's formed at outcrop has detached from the basement. The basement is undeformed at depth. But what about this basement over here as we go further in towards the Alps? Here the basement is deformed, and you can see on the cross-section that there's some thrust structures, but also the basement's uplifted to outcrop, whereas beneath the Jura and subalps, well, it remains beneath that depth. Well, let's go and look at the outcrops of basement. They make some pretty spectacular terrain. So here we are still in the French Alps. This is the Lamège group in the Écrin area. Those high peaks at the back are crystalline basement, gneisses and migmatites and granites. Well, let's look at one of these hillsides. Let's zoom in beneath those rapidly retreating glaciers. And there's a contact through there. The darker grey crumbly material is sedimentary cover, and the browner, lighter coloured hillside is basement. And there's a contact we can trace through here, which is a thrust. It's generally referred to as the Lamège thrust or Lamège thrust. Let's step back and see where it goes. There we go. So the thrust carries gneisses and granite, basement rocks in other words, over Jurassic strata, which are these slaty looking materials that lie lower on the slope. Where the label is, it's covered by scree, but you can see them in the ravines and on the crumbly cliffs to the left. So thrusting of basement onto sedimentary cover. So if we step back and put this onto a crustal scale cross section, the pink rocks are basement, the cover rocks are not coloured in on here. We can see this idea of a thrust that's carried basement high up over the sedimentary cover. Let's try and unravel this cross section. This shows what it looks like with a series of pre-existing normal faults that presumably accommodated some stretching before the Alps were formed, that have then been shunted back up as the crust has thickened during the collision process. It's formed the Lamèche thrust, but also the surrounding basement is deformed and sheared, and that's represented by those elliptical shapes. But as we go west, the idea is that the basement is undeformed, so that our elliptical shape actually is still circular. So we're implying that the crust out towards the west, towards the European foreland, is undeformed, but deformation increases to create the thickened crust and now the elevated ground, the high ground, so that we see these rocks at outcrop as we go east. But it's not just thrusting, there's also distributed strain in the basement. Now, a really great place to spot this is if we go around the Alpine chain a little way and into Switzerland. Here we go. Iconic photograph on the left of the north face of the Eiger, and the Eiger represents the left-hand slope of the cross-section, where those blue Jurassic rocks form that steep hillside. Well, that's what the north face of the Eiger is made of. But behind it, they're basement rocks. So on the cross-section, which would be perpendicular to the cliff we're looking onto on the photograph, you can look behind and see basement in the pink that forms those rather bulbous shapes. Well, the purple veneer that partially envelops the basement are Triassic rocks. Now, we can unravel those bulbous folds. And this is what we find, that the basement cover contact originally was faulted by normal faults that presumably controlled the deposition of the Jurassic strata. Of course, we can use the shape of the folds in the cross-section at the top to infer the relative competence, viscosity if you will, between basement and cover at the time of deformation, and the basement is behaving more competently than the Jurassic rocks. The Jurassic sediments are limestones, they're behaving more weakly than the basement, so they form the pinches. The more competent basement is forming the bulbous noses. But the folds themselves are nucleating, or at least the synforms are, the synclines, are nucleating on the little half-graben that we can identify in the undeformed section. Either way, it implies a lot of strain in the basement. So we can put this together on our simplified Alpine crustal scale cross-section to show that as we go from west to east in the basement, there's increasing strain. The crust is increasingly strainable as we go from west to east into the main part of the Alps. But what happens in the internal zones? Well, let's go and have a look. Here's a classic peak in the middle of the internal zones, the Monte Rosa chain near Zermatt. And here's a cross-section through that ground, and more besides, that was put together by Émile Argon in 1916, the same year that Auguste Buxtoff published his cross-sections through the Juror that we've already seen. But the sectional style here is radically different to the Juror. We can see that the basement, which here is shown in white, is intensely folded into those great tongue-like shapes. Above 1916 in the label, you can see that the scale of this cross-section, well, that's 10 kilometres. So those tongues, where it says Monte Rosa Nap, are 20 or 30 kilometres long, great long tongues of basement wrapped by various types of sedimentary cover, now metasediments. So complex tight folding of the basement cover contact. And if we zoom in and look at the state of the basement in the Monte Rosa Nap, this is what we see. Intense foliation in these algal gneisses. So intense ductile deformation at all scales in the internal zones of the Alps. So let's put this together a bit. We've seen on our tour that the outermost parts of the Alps in the west, there's decoupling of basement and cover. The sedimentary cover makes a fold and thrust belt, but the basement is undeformed at depth. But as we go a bit further in, we saw that the basement and cover are tightly folded in the vicinity of the mountain of the Eiger. And we've seen that at Lemage there are thrusts that interslice basement on cover. But then as we go back further into the internal zones of the Alps, rocks that were once deeply buried when they were deforming, everything is ductile and basement and cover are tightly infolded. So perhaps we can relate this to strength-depth profiles. So as we move into the Alps, maybe the crust deforms weakly, but there's still contrast between basement and cover. But as we go into the internal zones, it looks as though those rheological contrasts between basement and cover are depressed. Those conditions are achieved because the European rocks that now constitute the deformed internal zones of the Alps deformed beneath a thrust sheet, which provided additional burial and enhanced temperatures. The rocks there were deforming under metamorphic conditions. Consequently, we have different styles of cross-section from place to place through the Alpine chain. So that's a quick look at how deformation changes as we go from the outer parts of the Alps into the internal zones. We've seen how the structural style changes as represented on cross-sections and at outcrop with different deformation fabrics and different folding styles. Basement and cover can deform in different ways, but as the rocks heat up, they tend to deform increasingly in a similar fashion. So different rocks can deform with different types of structures, but different burial conditions and their related distinctly different temperature regimes also controls how these structural styles change. So the Alps remains a great playground for structural geologists, and it's a great place to find out how rocks deform in and out of a mountain belt.